Today, we tackle a problem that challenges us to find a specific kind of subsequence. Given an array of numbers, can you identify the smallest possible subsequence whose sum is strictly greater than the sum of all the numbers not included in it? The task is to return a subsequence from the input array, such that its elements are in non-increasing order. The key condition is that the sum of elements in our chosen subsequence must be strictly greater than the sum of all other elements in the original array. If multiple such subsequences exist, we need the one with the minimum size. If sizes are equal, pick the one with the maximum sum. The problem guarantees a unique solution under these rules. A brute force approach would involve generating all possible subsequences. For each subsequence, we'd calculate its sum and the sum of the remaining elements, then check our condition. This involves iterating through 2 to the power of n subsequences, and for each, potentially iterating through the entire array to calculate sums. This quickly becomes intractable for larger inputs, leading to an exponential time complexity of O, 2 to the power of n, and big O of n space to store and compare subsequences. Clearly, this isn't efficient enough. The key insight here is greedy. To satisfy the sum condition with the minimum number of elements, we should always pick the largest available numbers first. This maximizes our subsequence sum fastest. So, the first step is to sort the entire input array in ascending order. Next, we calculate the total sum of all elements. Then, we initialize a variable for our current subsequence sum and an empty list to store our result. We iterate through the sorted array from the largest element downwards. In each step, we add the current largest number to our subsequence sum and append it to our result list. Crucially, after adding each number, we check if our current subsequence sum is strictly greater than the remaining sum, which is total sum minus current subsequence sum. If it is, we've found our minimum subsequence and can stop, returning the result list. Let's trace this with the example, numbers 4, 3, 10, 9, 8. First, we sort it, 3, 4, 8, 9, 10. The total sum is 34. We initialize our current sum to 0 and an empty result list. We start with the largest element, 10. Add 10 to current sum, so it's 10. Add 10 to result. Is 10 greater than 34 minus 10, which is 24? No. Next, 9. Current sum becomes 19. Add 9 to result. Is 19 greater than 34 minus 19, which is 15? Yes. 19 is greater than 15. We've met our condition. We stop here. Our final subsequence is 10 and 9. This is correct because 10 plus 9, which is 19, is strictly greater than the sum of the remaining elements 3, 4, and 8, which is 15. You'll spot this greedy pattern when you need to find a minimum or maximum quantity by making locally optimal choices, especially when a sorted order helps satisfy a cumulative condition. Look for problems asking for the smallest number of elements or largest sum under a specific constraint. Time complexity is big O of n log n, linearithmic time due to the initial sorting step. Space complexity is big O of n to store the result list, in the worst case where we pick almost all elements. This greedy approach is efficient and straightforward. Try the next problem, same pattern. Don't forget to like and subscribe for more DSA insights.